The Big Freeze is the most probable theory for how our expanding universe will come to its end. Considering the inward pull of gravity, one would assume that the expansion of the universe was slowing down. However, as Edwin Hubble discovered while observing stars in nearby galaxies, the expansion is actually accelerating. All but our neighbouring galaxies appear to be moving away from us, with the most distant galaxies moving the fastest. Eventually, space will be expanding so quickly that the rate of expansion will be faster than the speed of light. The hypothesized repulsive force pulling stellar matter apart is referred to as dark energy, which is estimated to make up roughly 68% of the universe. New space is created equally between and within galaxies, but within galaxies, gravity is strong enough to hold planets together, at least for now. But what happens when dark energy overpowers gravity, or vice versa? The outcome all depends on a few factors: the universe's shape, whether it's open, closed, or flat, the true amount of dark energy in the universe, and the expansion rate. There are three possible outcomes: the Big Rip, the Big Crunch, and the most likely outcome, the Big Freeze. To understand the Big Freeze, we must first take a look at the less likely options. The Big Rip will occur if the force of universal expansion becomes stronger than that of gravity. Unable to compensate, gravity would snap like an overstretched rubber band, causing matter to go flying all across the universe. With the force of gravity breaking, the universe would destruct in the order of largest to smallest matter, from stars to the very atoms that make them up. This would lead to a universe full of wandering atoms in which no particle would be fast enough to interact with one another, among an expansive, mostly empty space. In the case of the Big Crunch, gravity would bring the expansion to a halt, then pull everything inwards, effectively reversing expansion. This would happen if there is less dark energy in the universe than we currently think, allowing gravity to gradually gain dominance over the expansive force of dark matter. As gravity pulls everything into each other, galaxies would rapidly collide, temperatures would rise, and everything would compress into a dense, hot, compact singularity, almost resembling the universe before the Big Bang. This could be the phase that makes way for a new Big Bang, sending our universe through an infinite cycle of death and rebirth known as the Big Bounce. Although these theories are all credible, current observations suggest the Big Freeze to be the most likely possibility. In the outcome of the Big Freeze, gravity would simply lose its force against the pull of dark matter, leading to all elements in the universe dissipating. Everything would continue to slowly separate as they are now, but without the pull of gravity keeping galaxies and planets together. Galaxies would dissolve and the universe would reach a zero thermodynamic free energy, unable to sustain new motion and life until all that is left dies out and the universe goes dark. One of the most important factors in the Big Freeze theory is entropy, the tendency for matter to decay and spread out into equilibrium. Higher entropy refers to something disordered, with low energy, such as a gas, while low entropy refers to something ordered, in a higher energy state, such as a solid. The second law of thermodynamics states that entropy increases over time, thus proving the likelihood of the universe to lose its gravitational force and dissolve into free space. As entropy in the universe increases, energy, such as heat, decreases, leading to a cold, bleak universe full of burnt-out stars, cold, dead planets, and black holes. 100 billion years into the Big Freeze, expansion will be so rapid that light from distant galaxies would no longer reach the Milky Way. In 1 trillion years, the local galaxy group will have merged into a single massive galaxy. In 100 trillion years, we will enter the degenerate era, in which all stars in the universe will die. In 10 to 100 quintillion years, stellar remnants will either escape their galaxies or be sucked into supermassive black holes at the center of them. In a decillion years, we will be in the black hole era. Space will be dominated by black holes. In a googol years, the last black hole will evaporate through Hawking radiation. After eons of expansion, cooling, and energy loss, eventually there will be only diluted gas clouds of photons and light particles until even these decay. Entropy reaches maximum, and the universe is dead forever. All activity in the universe ceases to exist.